Hi guys, today we're going to talk about the gas laws. So gases are unique in the states of matter because while solids, the particles are very close together, they're nice and tightly packed, and all they kind of do is vibrate around. Liquids are still very close together, although they are free to move around over each other, which is why they take the shape of their container, and solids keep their shape. Gases have lots of space in between them. They move around, they take the shape, and they take the volume of the container, and because of that, gases can really be expanded or compressed, heated and cooled, pressurized and unpressurized, add more and take some away. Lots of things that you can do with gases, and there is a great deal to learn from them. So as we have learned before, we have standard temperature and pressure, or STP, which is 273 Kelvin, or one of these guys here. Remember, a millimeter of mercury is a torr. It is the same thing there. Why is a millimeter of mercury a torr? It's because of this guy. His name was Torricelli. And in the 1600s, he created the first barometer. So this guy here is called a barometer. And what he discovered was that if he took a glass tube and inverted it into, created a vacuum in it, and then inverted it into a pool of mercury, on some days where there was high atmospheric pressure, that atmospheric would press down and then it would push up, and you would get a height of 760 millimeters of mercury out of it. So on normal pressure days, it would be 760 millimeters. On high pressure days, when there was lots of air pressure, it would go up and it would be a little bit higher. On low pressure days, it would be a little bit lower. And so basically the reason that we use the idea of height to measure pressure is because back in the 1600s, this guy here figured out how to measure the atmospheric pressure on a particular day by how high this column of mercury went. Why mercury? Because mercury is extremely dense. If you were to use a less dense liquid, this column might be 30-40 feet tall. And so consequently, if you use mercury, then you can get it to under a meter. So, all of these gas laws are ones that I know that you learned in first year chemistry. So I'm not going to spend a great deal of time with them other than to remind you what their relationships are. So our first one here is Boyle's law. So Boyle's law shows that there's an inverse relationship between pressure and volume. So in this guy here, your volume is high and your pressure is low. This guy here, if you put more weight on, so you put more pressure on, you'll notice that the pressure is high, and consequently that smushes everything down and the volume is low. So consequently, for Boyle's law, you have an inverse relationship. If you have high pressure, high volume, you have low pressure. And that's here, right? If you're in this spot there, then you are at high pressure, but then you are at low volume. So if you are at high volume, you are at low pressure. High volume, low pressure. If you are at high pressure, then you are at low volume. Or you can get a straight line out of it if instead of graphing it pressure versus volume, you do pressure versus the inverse of the volume, which is why it's called an inverse relationship there. All right, so the whole idea here is that as volume goes up, pressure goes down. As volume goes down, pressure goes up, and vice versa there. Then you got Charles's law, and what Charles's law says is that if you increase the temperature, you're going to increase the volume, assuming that you're at the same amount of pressure. So you'll notice that I've got two weights here and I've got two weights here with a movable container. If I crank up the temperature, so this guy here is a high temperature, so again, this is temperature going up. and this is low temperature. Temperature is going down. When the temperature is high and the temperature has gone up, the volume is also high. This guy here, the volume is very low while the temperature is low. So that is a direct relationship here, volume and temperature from each other. Now the only thing is here that this temperature must be in Kelvin. Why? Because if you start to do things like, well, I'm going to double the temperature and I'm going to double the volume, you've got to make sure that you are using a temperature scale that is appropriate for that. And Celsius and Fahrenheit are not good to use in this. Why? Because they're not absolute scales. In both Celsius and Fahrenheit, 0 really is not 0. What do I mean by that? Well, you can get to 0 in Celsius and you can get to 0 in Fahrenheit and still go lower. You can have negative numbers. And if you can have negative numbers, then 0 really isn't 0, which is why when you use these equations, everything must be in Kelvin. So if you want to use any of these equations at all, your temperature must be in Kelvin units, otherwise you're not going to get the right answer. So you can't use Celsius or Fahrenheit. First of all, you're never going to see Fahrenheit in this class. But if you are given to you in Celsius, you have to make sure to remember to take degrees Celsius plus 273 to get you the Kelvin temperature that's there. All right, our third one here is Gay-Lussac's law, and Gay-Lussac's law basically says that the temperature and the pressure are proportional to each other. So if you are in a condition where your volume cannot change, so you notice here we've got a rigid container, so our container is not moving here. This here is at low temperature. This here is at high temperature. Our volume is the same from both of those, but in our first case, our pressure is low, and in our second case, our pressure is high. So as pressure goes down, temperature goes down, or temperature goes down, pressure goes down. As temperature goes up, pressure goes up, and versa versa there. Our last one here is Avogadro's law. This is the easy one to know. Avogadro's law basically says that the volume is proportional to the number of moles. So if you have a certain number of moles and you increase those number of moles, then your volume is going to go up as well. So if you increase the number of moles, you are going to increase the volume. Unless the volume can't move, and in which case you'll be increasing the pressure instead. All right? So all of these guys then go together, and you have P1 V1 equals P2 V2. That's Boyle's law. And then you've got P1 over T1 equals P2. That's Gay-Lussac's law. And then you got V1 over T1 equals V2 over T2. That's Charles's law. And then this guy over here is Avogadro's law. And I don't know that specifically they're going to ask you about any one of these specifically. They're not going to say which of the following is Boyle's law. But they are going to expect you to understand that if the volume doubles and all other factors are the same, then the pressure is going to get cut in half. They are going to have you understand that if the temperature doubles and all other factors remain the same, then the pressure is going to double. They are going to expect you to understand that if you double the temperature of something at constant pressure, then the volume is going to double, and they are going to expect you to understand that if you pump in more of a gas, then the volume is going to go up as well. But all of these guys can really kind of be summarized by this. This is called the combined gas law. And the combined gas law is all of these laws shoved in together. So you'll notice P and V are next to each other here. P and V are next to each other here. T is underneath V and P. Sure enough, T is underneath V and P there. And then the N, the moles, is underneath V. Sure enough, it's there. So the combined gas law is just all of these guys together. And I suppose they could give you questions where they give you 4 different variables and then change 3 of them and expect you to figure out what's what. But I doubt it. Why? Because really the combined gas law gets kind of annoying when you start to get to lots and lots of these different variables. So instead what we are going to do is, instead of doing the combined gas law, let's take a look at what happens if we forget kind of half of this whole thing. So let's forget this for just a second. Let's ignore this guy here. Forget that this guy even exists. And let's shove our typical STP circumstances in to this equation and see what happens. Let's take STP and plug it into this equation. So my pressure is going to be 1 atmosphere, and my volume is going to be 22.4 liters. Remember that? And that's assuming I have 1 mole of a gas, and that's assuming I am at 273 Kelvin. Now get out your calculator, and if you get out your calculator and do 1 times 224 divided by 1 and 273, you get the following number, 0.0821. And that number, 0.0821, is called R, or it is the gas constant. Because all of these things are intertwined with each other, if I just take each of them at their appropriate standardized conditions and plug it in, I can now figure what any one of these things are given the other factors and knowing that R is 0.0821. So what I have now is I have the ideal gas law, which is what this guy here is. This is the ideal gas law, and where PV is equal to nRT. And R is just known as the gas constant. And it's just a number. And it's a number that will be given to you, but it is a number that can take a variety of different forms. Here is a table that's got all sorts of these different things. So if you are in, millibar liters per mole Kelvin, or bar meters cubed per mole Kelvin, or if you're in kilopascal meters cubed, it all depends on what units you use. And if you use different units, then you're going to have to use R that is appropriate. Now, I wouldn't worry about this because there's only 2 of these that I think are going to come up again and again. The AP test is going to make it so that the most common that you're going to see is going to be this guy. That's your 0.0821. And then this guy here, this is the same thing except that it's with torrs, or millimeters of mercury. So basically, guys, if you are talking about R, you're going to use 0.0821 if you are in liters, atmospheres, moles, and Kelvin. If you're not in liters, get to liters. If you're not in atmospheres, get to atmospheres. If you're not in moles, get to moles. If you're not in Kelvin, get to Kelvin. Or if you prefer, you can have R be the 62.36, and that's going to be liters, millimeters of mercury, because remember, a torr and a millimeter of mercury is the same thing. So liter millimeters of mercury per mole Kelvin, that is another very, very common one that you could use as well. I will be using both of these interchangeably. If the problem mentions atmospheres, then I'll be using 0.0821. If the problem mentions torrs, I will be using 62.36. Or if it mentions millimeters of mercury, I will be using 62.36. So the R is interchangeable, just don't use the 0.0821 if your problem is in millimeters of mercury. You'll get the wrong answer. Don't use 6236 if your pressure unit is in atmospheres. You won't get the right answer. So let your pressure unit kind of dictate what is happening there. If it's in atmospheres, use 0.0821. If it's in millimeters of mercury or torr, use the 62.36. So what kind of sample problems are there? They're quite simple. This one here says what pressure is required to contain moles of nitrogen in a 4.2 liter container at a temperature of right? So what have we got here? We have got PV is equal to nRT. So let's go ahead and plug things in. Now pressure, that's my X. That's what I'm interested in. Now the volume, they told me was 4.2 liters. So here is 4.2 liters. My moles, they gave it to me. So that was 0.023 moles. My temperature, they gave me as 293 Kelvin, because remember, you have to take that Celsius and turn it into Kelvin. So that's going to be 293 Kelvin there. And then my R, because I am in... you know what? I can choose. It doesn't even say. So I can choose the 6236 or I can choose the 0.0821. I can choose either of those that I wish. So my go-to is always 0.0821, and that's in liter atmospheres per mole Kelvin. So I now pick up my calculator and I do the mathification on this. 0.023, 0.0821 at 293, and then 4.2 liters gets me a pressure of 0.132 in atmospheres as my answer there. If I instead had picked the 6236, no problem. So I would have done 6236, and that would have been liter millimeters of mercury per mole Kelvin. And I would have gotten a different number, but the same answer. 0.023 times 6236 at 293 divided by the 4.2 gets me, that can't be right, 0.023 at 6236 times 293 divided by 4. There we go, about 100 millimeters of mercury. So those things are the same answer. It's just a question of what unit you have it in. All right. Number two says oxygen gas is collected at a pressure. I gave you the volume. I want to know the temperature for this guy here. So this is PV is equal to nRT. So the pressure I gave you here, the pressure is 1.21 atmospheres. The volume I gave you, that is 10 liters. The moles I gave you, it's 0.5 moles. Because I am in atmospheres, I am forced into 0.0821 for liter atmospheres per mole Kelvin. Now, if I want to use the 6236, that means I have to change this number so that that number is instead in millimeters of mercury. That looks like a pain to me, so I'm just going to use the 0.0821. And the temperature is what I'm interested in. So 121 at 10 divided by a half and 0.0821 gets me a temperature of about 295, but that is 295 in Kelvin. If I want that in degrees Celsius, then remember I'm going to have to subtract 273 from that, and that is going to be about 22 degrees Celsius there. Number three says how many moles of chlorine gas would occupy that volume at that pressure and that temperature, and then calculate the grams. All right, so again, we've got PV is equal to nRT. I've got a pressure of 4,500 torrs. That was given to me in the problem here. I've got a volume of 35.5 liters. That was given to me in the problem. N is what I'm looking for. I'm going to use 62.36 because they gave me this in torrs, which is the same thing as a millimeter of mercury. So this is a liter torr per mole Kelvin. And then they gave me the temperature as 373. Come on. What's going on here? Really? Sorry, had a little moment there with my iPad. So they gave me the temperature as 373 Kelvin there. So this is 373 Kelvin. Yay, technology. Awesome. And so now what I do is I solve for N. So 4,500 times 35.5 divided by the 6236 and the 373 gets me that N is equal to 6.87 moles. But it doesn't want moles, it wants the grams. So this is for chlorine, which is Cl2, and that is 35.5 twice. So that's going to be 71 grams per mole. So that guy times 71 is going to get me 488 grams of chlorine. So that is the ideal gas law.